We finished studying one electron atom, and we study many electron atoms. Then we discussed some new terms that are associated with many electron atoms. And then next class we will have some PowerPoint presentation about properties of atoms, which probably takes like 30 minutes, and we'll finish the chapter 1. Next Tuesday we'll start chapter 2, and Friday will be again chapter 2, and the next Tuesday, which is approximately around 5 plus 12 plus 5, around 17th of October we will have that quiz first on the chapter 1. I tell you on Friday exactly when it is. Okay, let's start today discussing the electronic states of hydrogen atom, but you know that I can write here hydrogen-like atom. And we know that every electronic state is characterized by quantum numbers, by n, l, m, sometimes people add here ml, s, and ms. So this is magnetic, angular, magnetic, spin quantum number. This one we always said is equal to 1/2. This one we said is equal to plus or minus 1/2. This one was equal to 1, 2, 3, and so on. This one was equal from 0, 1, up to n minus 1. This one was equal from minus L through 0 up to L. So now specifying 5 numbers gives you electronic state of a hydrogen. It means that if we make the boxes that we made last time for the 1s, 2s, 2p, 3s, 3p, 3d, and so on, writing a set of 5 numbers means like putting arrow here or here or here or here. So the lowest energy, 1, L equals 0, M equals 0, S equal 1/2, ms equal plus or minus 1/2. In fact, turns out that this lowest energy state is doubly degenerated. It means there are 2 orientations of the electron spin which have exactly the same energy. And we write it down for the 1/2, and the other possibility, n equal 1, L equals 0, M equals 0, S equal 1/2, ms equal minus 1/2. We write in a similar way with the arrow down. Now, these 2 states have the same energy, but only if there is no magnetic field. If there is magnetic field, they don't have the same energy anymore. The lowest energy state of any atom or for any molecule is called ground state. Everything what is not ground state, which has higher energy, is called excited state. And of course, the excited states would be what? If I take electron from here and put it here with spin up or spin down, or put it here with spin up or down or here. So you see that for hydrogen atom, there will be 8. 1, 2, 3, 4, 5, 6, 7, 8 excited states with the same energy. And again, I can write all these quantum numbers for the excited states, but as you see, this is not very convenient. It requires writing, a lot of writing. So very often, instead of writing all these things, people are writing this in a short way. So instead of writing 1, n equal 1, people just write 1. Instead of writing L equals 0, M equals 0, people are writing S. Instead of writing this, people are putting an arrow up here. Similarly, for the other state, it's 1, S, and the arrow goes down. Alternative way of writing the same thing goes like that. Again, you are writing 1, you are writing S, and instead of writing arrow up, you just say alpha here. And for the arrow down, you say beta. Okay, you agree that this is much shorter than writing all the numbers, but the meaning is exactly the same. So what are the excited states? The lowest excited states would be 2s arrow up, 2s arrow down, 2px arrow up, 2px arrow down, 2py, 2py, 2pz, 2pz. These are the 8 lowest. But of course, there are next excited states that would start with the 3. 3s up, 3s down, all the way of the p. Then of course the d starts. dz square up, 3 dz square down, all the d orbitals. How many of them? Infinitely many. How many people are observing? That's a different story. I think that for hydrogen atom, how many can be observed? N can go to something like 20 up. There's really huge number of states that can be observed. Good. We start the next story. Many electron atom. Well, the story is simple, right? What you would do, normally you would write the Schrödinger equation for x1, y1, z1, x2, y2, z2. You see that this is a 6-dimensional function already. So taking 6 arguments, positions of the first electron, positions of the second electron, and giving you one complex number. This would gives you energy times the same function, the same arguments like here. So we would write the operator, of course. In the operator there would be the kinetic energy of the first electron, so which is h squared over 2 mu of the first electron z1 square plus the same for the second electron plus the potential energy. So potential energy, that would be what? That would be Ze with the minus charge electronic divided by the position of the first electron. If I'm using the x coordinate, let me use the x coordinates. That would be x1 square plus y1 square plus z1 square. Okay, here is a minus. Let me write this minus here. So it would be minus. And here would be the minus 2. And here it's for the other electron. So again, Ze square x2 square plus y2 square plus z2 square. So again, kinetic energy of both electrons, interaction of the first electron with the proton, interaction of the second electron with the proton, and of course the electrons interact with each other. So it's a repulsion this time. We have E square, and here we have x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square. Good, finished. Now the equation doesn't look so bad. Really the new part is only this part, but since this part is here, turns out nobody knows how to solve this equation. The situation is even worse. From the classical mechanics, we know that for the problem of 3 bodies, there is no solution, no exact solution. So if you have 3 bodies, such equations cannot be just solved. No analytic solution is known, no closed form solution. So the only thing that can be done, you can do some approximation on this. For example, one of the approximation is forgetting this part, solving this equation, and then including this part inside the solutions. That's not for this class. That's a bit difficult. But anyway, this equation cannot be solved. Nobody knows how to do it. Already for 2 electrons. For 3 electrons, 4 electrons, 5 electrons, the same situation. For any molecule, the same. The Schrödinger equation cannot be solved. We don't know how to do this. And there are many different approximative methods. Not exact, but approximative, giving almost the solutions. But this is the topic for the quantum chemistry class, not for the general chemistry. So we are just going to forget this, because there is no solution to this equation. And what I'm going to tell you now is what is happening to the orbitals, to the wave function of single electrons if you have more than 1 electron. The first thing is that 1s level, stays approximately the same place, but the 2s and 2p don't have the same energy anymore. 2s stays in the same place, but 2p goes up. So 2s, 2p. The same thing happens for the 3s. 3s, 3p goes up, and 3d goes even more up. So 3p, 3d. It goes so much up that it goes even higher than 4s. 4s is now a bit lower. And of course 4p would be here and 4d would be here. I'm not going to draw it. So how the wave function looks like? Well, you can think in the first approximation that if you have 2 electrons, then the wave function looks like that. Wave function for 2 electrons. I call it 1 and 2. That would be the wave function for the electron number 1 multiplied by the wave function times the electron 2. Now this and this doesn't have to be the same. Or even there is a Pauli principle. Sometimes called as a Pauli exclusion principle, saying that these two cannot be the same. So these two must be different. What does it mean must be different? It means that out of the 5 numbers, n, l, m, s, and ms, at least one of the numbers here and here must be different. If all 5 numbers are the same, this is equal to 0. So to avoid the wave function to be equal to 0, you have to put here some set A, and here maybe B. Now I tell you in secret that this is not the real way how the wave function looks like. The real wave function looks a bit more complicated. It has a minus sign here, and then it has A describing second electron now, and B describing the first electron. Now it's correct. What happens if I change the number of the electrons? If I change the first one, I call it 2, and the first one I call 1. If I do this, then you see that this one becomes 2, this one becomes 1, this one becomes 1, this one becomes 2. This would be exactly the same like this one, except that this minus will be now here. That this plus will become minus, and minus will become plus. So maybe I write it once again. Then it becomes what? A, 2, B, 1, minus A, 1, B, 2. If you compare these two things, you see that this and this is the same, except for the sign. Here's plus, here's minus. And again, this and this is the same, except for the sign. So what I found here is that this is equal to minus 1, 2. This is very important part, because it says if I have a wave function that describes 2 fermions, and electrons are fermions. If I replace the fermions, now the fermions are the same. If you have 1 electron and second electron,
and I tell you to close your eyes, you close your eyes, I change or I don't change, and you open your eyes, you don't know if they were changed or not. They look the same. But if you replace them, then the wave function will change sign. We say that the wave function is antisymmetric. Anyway, important part is that the wave function is changing sign by replacement. Now, what happens if these two are the same? It's AA. Then I have AA minus AA, which gives me 0, which is exactly the explanation of the Pauli exclusion principle, saying if two of them are exactly the same, then this is 0 everywhere. So there must be some difference. One must be A, one must be B. So one of the 5 digits must be different. Okay, coming back to the wave function, it looks like that. What is the lowest possibility here? Of course, the lowest possibility, and again, 2 electrons, that would be the helium atom. So the helium atom wave function would be given by 1s orbital with the spin up multiplied by the 1s orbital with the spin down. And again, you should remember about the antisymmetry. This describes the electron 1, this one describes the electron 2. So there must be, of course, the other term, 1s with the spin up describing electron 2 multiplied by 1s with the spin down describing electron 1. But this term always is there, so I always will be writing shortly. So one way of doing this thing is writing here the antisymmetrizer operator, that acting on this gives me also this term. Good. Again, this is a difficult part that you will learn in the quantum mechanics class. So you have this 1s, 1s. Good. You can write it very shortly on a plot doing just this. 2 electrons in the same box, one with the spin up, one with the spin down. What is the wave function for the next atom? So the wave function of the lithium atom is nothing else like the antisymmetrizer that I will be putting here. You know that it's making the other terms. 1s with the spin up for the first electron, 1s with the spin down for the second electron, and then what is the next one? Lowest. If you remember the plot, the lowest one was 2s. 2s with the spin up or with the spin down. Again, they have the same energy. So I just choose the option with the spin up. What is the next one? Lithium, that would be beryllium. Again, antisymmetrizer, 1s, spin up, 1s, spin down, 2s with the spin up, 2s with the spin down for the third electron, and here is for the fourth electron. Since people are lazy, and second, writing these formulas takes a lot of space, people are usually writing it shortly. They say helium, which is this part, and then 2s plus. This one would be written as helium. Why helium? Because we have this. And then would be 2s plus up, 2s down. Again, what I'm plotting here, the wave function, are not the solutions of the equation that I wrote a moment ago, because we don't know the solutions of these equations. These are approximate solutions. let's say 90% good. Okay, let's do some another example. Let's take neon. Neon has 10 electrons. So what can I start to write with for neon? I start with helium, of course. Helium gives me 2 electrons. Then I'm writing 2s up, 2s down, 2px up, 2px down, 2py up, 2py down, 2pz up, and 2pz down. Again, long. Too long. What people do? Well, like always. They say that this is nothing else than helium. 2s with 2 electrons. If 2 electrons, one must be up, one must be down. 2p with 6 electrons. Okay. There must be px, py, pz, px, py, pz, 6 electrons. This is much shorter. There is a problem. Of course, like always. If I have carbon wave function would be helium. Carbon has 6 electrons and 4 electrons. So of course 2s2, this is clear, the lowest box. And 2 electrons are left. For the 2p. How can I put them? Well, you see that if I have 1 electron, probably it doesn't matter if I put it here, here, or here, and I put it up or down. Probably that would have the same energy. Doesn't matter. But if I have 2 electrons, the possibilities are to put it like that, to put it like that, and to put it like that. If you look at this, you may feel that this is not the same. Probably if I plot another one here, and I put one here and one here, you can tell me that this is maybe the same, because if this is px, this is py, and this is pz, and this is px, this is py, and this is pz. So for the person who stands on the y-axis, this wave function looks the same like for the person who stands on the pz axis, this wave function. So these two maybe are the same, but these clearly have 2 arrows up, and this is 1 arrow up, 1 arrow down. It means that here for the 2 electrons, the magnetic moment is in the same direction. In this case, the magnetic moment is opposite direction. So the magnetic interaction between electrons would be different. Here, not only the magnetic interaction is opposite direction, but they are also at the same place of space. And turns out that yes, they have different energy. In experiment you can clearly see the difference between them. So these things we are writing here are called electron configurations. These possibilities that I'm discussing here, this is what really is observed in experiment. And it's called atomic terms. And unfortunately, we don't have time to discuss it, even it's something very, very interesting. So turns out that these two, okay, so for carbon we have 2p with 2 electrons. But now saying 2p with 2 electrons, we are not saying this, this or this. It is not clear which of them we mean. So the electronic configuration or electron configuration is not perfect thing. These atomic terms are much better description of the many electrons atoms. So you have to remember one important thing in science. When a small child is learning about physics and chemistry and asks you a question, sometimes you want to explain, but you understand that if you explain the real answer, the child will not understand. So you are telling the simplified answer. Sometimes it's a lie, or always it's a lie, because the child cannot understand the truth. Unfortunately, with chemistry, it's a similar story. Your book is telling that electron configuration is a real story. No, it's not. Atomic terms are the real story that is observed in an experiment. And many things in this book is like that. And many things I'm teaching you is like that. Because I know that there is no way of explaining you the real story. So I'm lying. I know that I'm lying, and I'm not telling you I'm lying. This is not good. So later in the future, when you learn deeper mathematics and deeper physics, many of these things will be not exactly the same way I taught you. But the reason is that being 19 years old and having not much mathematics, university mathematics learned, you are just not able to understand the real mathematical structure of the theory. I'm sorry for this, but I try sometimes to tell you, like now, where the truth is, but still we cannot study this because it will take us 1 hour. It's very simple, but it takes 1 hour to understand how to find electronic terms. So, if you think that energy of this one would be 1, turns out if you go to atomic terms that this one electronic configuration in fact has 3 different energies. And the differences are relatively large. Good. You know now the electronic structure of the many electron atom. The important thing is to remember how these are ordered. So we go. We have 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 5g. Nobody's seen g electrons, but still we know that this is good solution, so we'll write it down. 6s, 6p, 6d, 6f, 6g, 6h. 7s, 7p, 7d, 7f, 7g, 7h, 7... I really don't know what is next. Probably J. I think there is no I. But maybe I. I mean, it doesn't matter. Okay, so if you have 57 electrons, how to write the electronic configuration? You put 2 electrons here, then you go here. 4 electrons, then you go down. So 2, 4 plus 6, 10. Then you come back to 3s. Then you go down. Already 20. Then you come back here, 22. Then you come back here. It's 10, so it will be 32. Then you come here. It's 38, 40, 50, 56, 58. Okay, that's too much. 57 we wanted. So we finish. We put all the possibilities here and finally one electron on 6s. Okay, but let's say we have 99 electrons. What is the order? Well, then from 6s we go here to F. Then we go here, here, here. From this one we come to F again. Come here, and as you see, the next one we would go to 8s. And after 8s, we would go to the G electrons. But as I said, nobody's seen G electrons, right? It's enough to look at the periodic table of elements, which is here. And you see that everything what we know finishes at 7, 7s. There's no 8s here. We don't know any elements starting with 8s. And you see that 5G comes after 8s. So maybe in the future, if we can find the next row, then maybe it's important to study the G orbitals. But for now, there is no such need. By the way, the structure of this period goes exactly the same like the yellow line there. So we have 1s, then we go to 2s, then we go to 2p, then we go to 3s, then we go 3p, then we jump to 4s. After 4s there is d. That's why there are d orbitals here. After d we go to 4p, which would be here, 6 of them. After 4p it's 5s. We are here. After 5s we come back to 4d. This 10. After 4d there is 5p, that would be that. After 5p 6s. 6s, after 6s there is F. Well, here there is some enigmatic 57 to 71. These are the F orbitals that, in fact, shouldn't be here down. They should be entered here. But if they are here, this table has long up to here. That's why people are usually lazy and print them down. But you should understand that the real structure of the periodic table follows exactly the pattern we had. So we can draw it very fast. We know that 1s and 2s comes here. Then we have 2s, that would be these two. So 1s, 2s is fulfilled here. Then we have 2p. 2p, I don't know what to do. Let me start one again. I hope that will be long enough. Start once again. 1s, 1s. Then is 2s, 2s. Then we are leaving the place for the F electrons. The F electrons, there are 14 of them. 1, 2, 3, 5, 6, 7, 8, 9, 10, 12, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would be the d electrons that I don't have still. Then I have the p electrons. 1, 2, 3, 4, 5, 6. This is the 2p. I mean, generally there is no reason why I cannot put them here. That would be still okay. But you see that later, now between s and p there is nothing. But later, between s and p, the 3d would be entering. So I'm leaving the place for them. So now I have nothing. I have just 2p. 2s, 2p, now is 3s. 3s. Next one is 3p. 3p. Next one is 4s. 4s. After 4s is 3d. These were d, so from here to here is 3d. Then I have 4p. Next one is 5s. 5s, 4s. After 5s, 4d. 4d and of course 5p. Next one, 6s. After 6s, finally f. So these are the f electrons. There would be 4f. Then it's of course 5d and 6s. After that, 7s comes. After that, the 5f comes. After that, I would be happy to say that 6d comes, but I have to do the dots up to head. 6d, because we don't know these elements anymore. So that's really how the periodic table of elements looks like. Not like that on the wall. That should be the real one, but it's too long. So one more change. Usually this 1s and 1s are not printed like that together. Usually one of them is taken away and put all the way up to here. The reason for this? Turns out that this element that is called helium with 2 electrons is very similar to elements that are located here. There would be neonium, there would be argon, krypton, xenon, and radon. Rd or Rn? Rn. So they have very similar properties. But I mean, generally there is no special reason why to put this one here. It should be there. Just by tradition, it's here. Good. Now, next thing. I know it's not nice to learn this, but you should know by heart the names of these elements, the names of these elements. It doesn't mean necessarily that I know, but you should know, because it may be during the exam. One of the questions. What is the 5th element in the D? First D. So you should remember them. Okay. This is called periodic table of elements. Okay, listen to this. Now we just discuss energetic stability of an atom. So we start with the mass, proton. The mass of the proton is equal to 1.0072766. Mass of the neutron is equal to 1.0086654. Mass of the electron is equal to 0.0021944. Of course, somebody will ask me what is the unit, and a very good question. So I tell you what is the unit. In chemistry, mass unit, very often abbreviated as the MU, is 1/12 of mass of a single carbon atom. You should be careful because in physics it's 1/16 of the oxygen atom. And they are different, of course. So you should be careful. When somebody says mass unit, you should first ask you, are you chemist or physicist? Then you can understand. But anyway, coming back to this one. So let's take an atom. The atom would be beryllium atom. Beryllium atom has 4 electrons and 4 protons. But the mass, atomic mass, the mass number is 9. It means there is 4 protons, 4 electrons, and there is 5 neutrons inside beryllium atom. You can calculate what is the total mass of beryllium using no. You can measure this one in experimental. So if you measure this in experiment, the total mass of beryllium atom would be 9.0122. Okay, now we know it's 4 protons, 5 neutrons, 4 electrons. Using these masses, we can calculate a sum. So it would be 5 masses of neutron plus 4 masses of proton plus 4 masses of electron. You can calculate this together and you find that this is equal 90746,278. These two numbers are not the same. They're not even close to each other. You can calculate what is the difference between them. So the difference between them is equal to 0.0624 mass unit. What does it mean? It doesn't make sense, right? We have the proton mass, neutron mass, electron mass. When we put it together, we get something else than the reality. What happened to the rest of the mass? Or where the rest of the mass is taken from? Well, the answer is like always simple. The mass and energy is the same. If you remember this, it means the rest of the mass transferred to energy. So we can calculate how big is the energy from this connection. So let's do the story once again. I take proton, I take proton, I take proton, I take proton, I take 4 electrons, I take 5 neutrons and put everything together. By doing this, instead of getting this mass, I'm getting this mass. So the rest of the mass, this one, was changed to energy. Now, using this equation, let's calculate how big is this energy. So if you plug everything together inside this equation, and you find that this is equal to 5.8 times 10 to the 7 of electronvolt. I mean, this doesn't tell you anything. This is just some number. So, but now, to understand how big energy it is, I tell you that you have to take 2.700 kilogram of coal and make a big fire. So you take so much coal, you make a huge pile and you put fire on this This is big fire and producing energy. So this amount of coal, you know what coal is? Can somebody say in Chinese? So much coal is needed for making one atom of beryllium, one single atom. This is huge. And this one can explain you why the atomic bomb has such a huge power comparing to normal chemical bomb. Because atomic bomb, what it's doing, there are two possibilities. One possibility is take a big atom and split into two small atoms. Another possibility is take two tiny atoms and make a big atom. This is called atomic bomb. This is called hydrogen bomb. But anyway, the idea is the same, of getting extra energy from extra mass. These are huge elements, huge amount of energy. Now, last question to this one. You have here 5 neutrons and 4 protons inside the nucleus, and you have 4 electrons somewhere in the cloud around this. Now, this energy is coming from electrons, protons, or neutrons. One way of checking this is just separating the beryllium atom, making 4+ ion, and separating 4 electrons. This is called ionization. This ionization requires amount approximately 10 to the power 3 electronvolt. Compare it with this number. It means that the energy only in electrons is very, very small. So all the energy, all this huge energy is inside the nucleus, which finishes our class. Thank you.